Dr. Marisa Monreal, who's a research scientist at Los Alamos National Laboratory, and she's going to be talking about molten salt research at Los Alamos.
I am a research scientist. I'm a chemist, actually, in the inorganic isotope and actinide chemistry group here at Los Alamos. We're in the chemistry division. And my background is in actinide chemistry, synthetic chemistry, actually. And I always make the joke that my background is in working at the highest temperature was 200 degrees in organic solvent. So when I made the switch over from my background, postdoc and graduate work to molten salt chemistry, it's quite a jump in temperature and solvent. But essentially, the chemistry, so the actinide chemistry in a solvent, is really the same fundamental properties and studies. And so finding an interesting new expansion to my career with all of this work. So it's a little bit about me. I'm going to talk today about molten salt research here at Los Alamos. And in particular, I'll be describing our efforts that my colleague Matt Jackson and I have been heading up over the past going on 5 years now. Okay, so just to start off, I wanted to just really briefly discuss why our institution is interested in molten salt research at all. So really for Los Alamos, this interest originates in the fact that as a lab with a weapons production mission, we have been using molten chloride salts for decades in the production of pure plutonium metal. So because of this tie and the fact that this is where our experience and expertise lies, our primary salt system is indeed chlorides. So that's why I've listed that there. But I do like to point out that we actually welcome and in fact have recently been awarded some internal funding for our collaboration to use fluoride salts in some of our recently developed R&D efforts. And I'll talk a little bit about that in a little bit. So on the bottom left there, I'm showing a flow sheet. It just demonstrates my statement up in green at the top there. What you're looking at is the conversion of plutonium oxide to 4,9 pure plutonium metal through several steps. Each of these steps occurs in molten chlorides, and each of them involves plutonium in various oxidation states and forms from oxide to chloride and metal. Therefore, our reason for interest is that these two areas, the molten salt reactors and plutonium metal purification, are overlapping, and they share all the pursuits that I've listed there on the right. I won't go through them all, but you can see everything from the preparation and characterization of solvent salts and plutonium trichloride, thermophysical and chemical properties, and the list goes on down all the way down to even identifying signatures and diversionary tactics. So all of those pursuits would benefit both of the fields, MSRs and plutonium metal purification. And so, in fact, the interest goes even beyond just that tie to pit production. Molten salt work ties to several other areas that are published in this kind of guiding document for our laboratory called the Lab Agenda. I pulled out some kind of key points here on the top right in this red and pink area. These are strategic initiatives that this work really falls under in our lab agenda. You can see that we have a big part here in the mission-focused science, technology, and engineering, in particular, developing and implementing an integrated nuclear energy and materials initiative, and developing and implementing integrated initiative for plutonium and actinide missions. I mean, those two right there pretty much describe molten salt research that we're doing. So it's nice to see that we are represented well in the current lab agenda. And then in the bottom left here, I see I've just listed all the areas where LANL is world leaders. We have world expertise in all of these areas, and they're all molten salt related. So it's nice that we have all this expertise co-located and great colleagues to work with. So before I get into the details of the work that Matt and I are kind of heading up, I wanted to just talk about some of other ongoing LANL molten salt related projects and programs. I'll just highlight a couple. So Jake mentioned NEAMS. It's very nice that we have David Anderson and Chris Stanek as our LANL fellow colleagues. We've benefited quite a bit from working very closely with David, as I'll talk about in a bit. And we've been greatly benefited by the support and lots of really helpful discussions with Chris. So that's great to have. I also wanted to point out that we have this DOE BES EFRC housed here at Los Alamos. Blas Ubaraga is the PI or the director. And in that future program, they're looking at the coupling between irradiation and corrosion. So right now that's not being applied to actinide-bearing molten salts, but we've had quite a few discussions of late with BLAS to collaborate in the very near future on this. So it's pretty exciting to think that we could bring these two research areas together. There's also up on the top right some kind of smaller projects, one that is looking at acoustic diagnosis and monitoring of molten salt systems, and then another that's using XAFs to do some spectroelectrochemistry. And so those are kind of areas where we're looking to collaborate and kind of complement. And then I wanted to point out something really nice. So in the bottom right of the slide, I've listed some defense programs and defense nuclear non-proliferation programs where we have existing collaborations here at Los Alamos. And one of these has very nicely allowed us to collaborate with Mike Simpson at the University of Utah, and allowed a very recent publication looking at the effect and measurement of residual water and calcium chloride. So I wanted to just highlight that. We just found out that it was published just recently in the Journal of Radioanalytical and Nuclear Chemistry. So with that, I wanted to get a little bit into the details of some of what we do. So at the top of the next couple of slides here, I've listed in yellow this initial LANL molten salt project. So really it just ended. So it was a little over a year's worth of work of this new kind of thrust at Los Alamos within the LDRD program called the Directors Initiative. So our lab director chose a few select projects. We're talking, I think, less than 10 for this kind of limited term but high investment projects to see areas of high interest for the lab, as I was describing in the lab agenda. And so we were lucky that we were chosen, and we really were able to further our work and get some of these things established on molten salt. And so kind of the first stuff I wanted to talk about here was what Jake was mentioning earlier, which is using LANS. So this is a neutron beam. It's a very unique capability that we have on site at Los Alamos. I really want to emphasize that this is on our site, so it makes it very convenient for us to be able to just prepare samples and drive them over and study them at the beam. Another really unique capability there at LANS is that it has the ability to look at actinide samples, up to and including plutonium. And then another thing we recently found out is that we can also place irradiated samples into the beam. So this is just a great opportunity that we wanted to take advantage of, and I believe we did pretty good with this, and we're continuing it on now. So in this density in a different way kind of work, we're using what we're calling neutron dilatometry. So this is basically a well-characterized stainless steel capillary tube, and I'm showing a photo of two of them in this assembly right here on the left and right, that's used to contain the fluid. And then what you're doing is you're measuring the volume of a sample of known mass at different temperatures using neutron radiography and image analysis. And so in this graphic here, basically you have the neutron beam focused on the sample that's held within the steel container. So we're taking advantage of the neutron's power to penetrate and image through the big furnace that's holding the sample molten. The detector is seated behind the furnace there. And this graphic is actually showing dynamic radiography, where you have a pulsed beam and lots of different images, and we actually use that for our viscosity measurements, which I'll show in a little bit. But here we're just, for density, we just use static pictures. So let's see. So I also wanted to point out this kind of interesting looking feature or shaped machined piece in the center here. This is what we're calling our neutron ruler. And so what that is it's basically just machined with precise dimensions, and that helps orient us and provides a reference point at any position along the length. And so what you're looking at here is a series of images stitched together. So you can see the ruler in the center and the capillaries on either side. And then here you can see kind of a zoom in of what the meniscus looks like at molten temperature. Our setup was calibrated with Fluorinert. It's just a material that we use as a calibrating liquid at a relatively low temperature, but across a range of temperatures. And we found that we could match with only a difference of about 0.05%. So we proceeded on to our molten salt samples. Here's just a quick picture of the schematic of that setup that I just showed you. So just to orient you again, there's that ruler and the two samples in the beam, the detector here. And here's some details about the beam and the camera. with these images, this is just a selected set of results. These are some typical images from our neutron DIL experiments. We clean these up by taking baseline images from the dark field, so no neutrons, to fully assembled, and then that helps us produce a clear image. Just to note, the lithium, potassium, uranium image at 393. So that's this one down here. You can kind of see a little bit of interesting features there, not such a nice clean meniscus like I showed on the previous slide. So I wanted to point that out because we found that salt wasn't fully molten despite 30-minute soak and exposure time. It actually takes quite a lot of heat energy to fully melt these, and this is something that we also observed in our DSC experiments. So this caused us to change our approach to heat the upper boundary of the experiment and then take measurements on the way back down to the liquid solidus point of the salt mixture. Just a little pivot there as we were taking data. And so with this slide, I just wanted to talk a little bit about how we do this image analysis. So initially, we just used it for straight up measuring the sample height change, but we now have developed this technique to fully map the volume of each salt studied. So this is done by carrying out image analysis to identify points of contrast with high resolution. And so what you want to just look at, you can follow the yellow line here. So it's going along the wall of the capillary. You can see that the contrast doesn't change much, it stays pretty flat. And then if you follow the teal colored line, which kind of goes down the center, crosses over the meniscus, you see a bigger change in contrast. So it goes from here to here. And so what this analysis does is it looks at the change in grayscale across that meniscus and across the X direction. It allows precise mapping of the meniscus location in both X and Y, and then we integrate over 2 pi, and that gives us precise sample volume. So I like to point out the bottom left here. So far, we've gotten an uncertainty down to about 0.9 to 1.2%. And we have some planned equipment improvement, the detector, the camera, et cetera. And we expect to lower this down to 0.7%. Just a summary of the molten chloride neutron DIL experiment data is here. So these are the densities versus temperature for all of the samples we've looked at. Uranium-bearing chlorides, for the most part here, both uranium and pure salt eutectics as well. And what our plans are next in our next project are to expand this range now this capability has been established. Something that Jake also mentioned was our integration with modeling. So this is for our work with David Anderson, and I just wanted to kind of give him a quick shout out at the bottom right here in green. Tomorrow afternoon session, he'll be talking a bit more about this. But just a brief summary on this here, you look at the top and the bottom sets of data, you have pure uranium trichloride and pure sodium chloride. You can see that the modeling data and experimental data are just about right on top of each other. But when you look at the center set here, when we started looking at mixtures, you see that the experimental data is different. And so we have some kind of within team discussions about higher or lower, depending on who you talk to. So we're still figuring that out. But the bottom line here is that it's different than just simple correlations will tell you, than just simple average density based on mass fraction. So what this is telling us is that modeling data is not as close for the mixture as it is for the pure systems, and it required the incorporation of van der Waals interactions and magnetism, for example. And this is actually prompting the next stage of our research. Just a quick summary here of the viscosity. So same idea using neutron beam, but now we're blending it with falling sphere. So we're just using the neutrons to visualize that. Just as a side note, if I'm being totally honest, we initially started out wanting to do viscosity first and then discovered some issues with sphere contrast. And so rather than trying to derive density from viscosity, we ended up just pivoting completely to the densometer that I showed you, or neutron dilatometry that I showed you, and then did a couple of measurements of viscosity. And this is an area where we'll be pursuing some next steps, some improvements in the apparatus. Here is a picture of this apparatus, and here I really want to give a major shout out to our postdoc and soon to be converted to scientist, Scott Parker, named down here, who took this drawing on a piece of paper to a prototype, a functional apparatus here in the beam, showed from the door of the flight path and from the beam's perspective in very short order. I showed you that the time frame of this project was rather short. And so this is the idea. You're dropping spheres. This is is my hand holding these spheres, 2 millimeters in diameter, through an actuator with a centering funnel. This is controlled remotely from outside the flight path, and then it's dropped through the molten material and detected by the neutron beam. So here's just some quick examples of the results. So we first started off again with our calibrating fluid. We found a relatively close match to the known viscosity and moved on to our molten salt sample from there. With this, we used uranium-bearing sodium chloride, and that's me loading the quartz tube for this experiment on the right here. And what I wanted to point out here is that what ended up happening is it was much faster through the molten salt than we expected. And so this was interesting. There was a couple of issues with this. So first off, it points to the difference from any plans you might have based on simple correlations. That's not going to work. Remembering too, there's no published data to compare this to. And when we were doing this, as I said, this was first. This is what we were trying first, and so we didn't even have our density yet. So all of this was based on what we could find in the literature. Samples that didn't have even actinide in them. We did our best, and it just turns out it was way too fast. So our next steps are going to be including apparatus improvements, sphere material improvements. We're even going to turn into a sphere manufacturer, I think, when I talk to Scott about this. And so that's going to be some interesting next steps there. Just a couple more slides on some of this. I wanted to talk, so Mel, I thought, did a fantastic job. Melissa did a great job talking about differential scanning calorimetry and highlighting some of the really, important challenges that can come across this. I think we were a bit naive when we first started off with DSC, thinking, oh, you have the instrument, should be fine. But no. And so over the course of this initial LANL molten salt project, we very carefully calibrated for high temperature, encountering some of the same things Melissa was describing. We have done that now. We've collected melt points for a range of molten chlorides, including uranium-bearing samples. We've made standards for our heat capacity measurements, and now we're ready for data collection, and that's coming up in the next couple of months. What I want to point out here is that we do have this instrument available in the Plutonium facility, and so we're ready to make those measurements once we get that material. Another kind of neat thing that came about with this work is that we can also use it for purity measurement. And so I really appreciated what Melissa was saying too about quality of sample. And this just kind of shows a nice, neat example about that. On the left here, we have a very nice clean sample of uranium trichloride, and the one on the right is not so pure. And so we use this as one of the many ways to make sure our samples are pure, and it's especially useful for our post-radiography experiments. We can bring in our samples and make sure they're still pure and they're still what they were when we put them in. A couple of slides, just wanted to talk about some neat spin-off projects that have recently been funded. Some of the exciting things about this is that as we've launched these capabilities, we've been approached to collaborate by our fellow colleagues at LANL. So just a quick description, this is just funded for FY21 by one of the Lance Beam scientists, and it's using energy-resolved neutron imaging to explore signatures for MSR safeguard security and safety. And what this does is you can kind of look on that bottom right here. Figures B and C are just illustrating how powerful this technique is to quantify and map isotopic distributions. And so Alex will be using this technique to explore the possibilities for safeguarding MSR technology. Another spin-off project is using neutron pair distribution function analysis. So this is neat. It's another technique at Lance where you can look at local structure. And so in NPDF, you look at the probability of finding an atom at a distance r from an atom in the origin. We can use it to look at liquid materials in addition to, of course, the crystalline. It gives you basically local order information, local structure information. And that's really helpful as we try to understand behavior changes on the bulk. And then finally here, the third spin-off project I wanted to talk about was that non-invasive acoustic sensing. So this was also just funded recently. It's based on some existing LANL technology that was recently licensed for room temperature monitoring of corrosion in oil pipelines. And so we've now, we're starting to look at expanding this to molten salt applications, in particular tying it to our Lance studies and doing non-invasive sensing of density and viscosity over a temperature range. And then just want to finish off with the latest news, and that is that we found out that we were awarded a 3-year project to really take that initial work I just described and just expand it out quite a bit. So I wanted to give a summary of our planned experimental efforts here. This is just a table of the properties that we'll be looking at. So everything from bulk thermophysical properties and local structure, down to local structure. There's some examples on the top right here. For example, drop calorimetry. We're going to be using electrochemistry. And then I wanted to kind of show off a little and brag on our LANS experiments that are literally going on right now as we speak. I got this data yesterday for expanding our established technique there, looking at mag chloride, sodium chloride eutectic. So it's kind of fun to see. I love the fact that we can get this data during this beam time, even despite some COVID delays. Since this is the chemistry session, I won't go over all of this, but I wanted to point out that we have a 3 thrusts of this project: chemistry, thermophysical properties, and mod sim. And in particular, in the chemistry section, we're going to be including actinides from uranium, thorium to plutonium, chloride synthesis, solvent salt preparation, and local structure studies, and then integrating that with thermophysical properties and mod sim. And I wanted to put a little shout out here. You know, we have lots of great scientists, 13 total, but we are going to be using our current postdocs, of course, and we'll be hiring in all 3 thrusts. So just wanted to get that out there to keep an eye out for some job ads that we'll be needing to post very soon for some help on this big project. Okay, and with that, I will finish up. I wanted to give some special acknowledgements to Scott Parker, who did most, if not all, of the density, viscosity, and DSC work and setup. Alex Long, who was really in charge of the LANS experiments and helps us with his expertise in image analysis. For funding, we looked to LDRD and the mRNR program. Here's my contact information and my colleague Matt Jackson's info. And I just wanted to put this link here. We had a very nice chance to have some pretty pictures taken in our laboratory. So this is us ladling some molten salt in our glove box. And if you'd like to read more about our work, you can go to this link and read all about it. And with that, I can take any questions.
Joanna Farland, who compliments you on a very nice presentation, wanted to know what's the pixel size at LANS, and have you seen any creep in your measurements or hysteresis in the density of measurements?
So I do have that. Let's see. Hoping that it was on my spec slide for that. I don't have that memorized. And so far in our measurements, the most kind of range that we were seeing was what I was describing with when we were going up and down in temperature. We did see that we needed to kind of go all the way to the top of the range of temperature first and then come back down to make sure that we were getting repeatability and actually the true meniscus and fully molten density. And I'm trying to see if I have pixels here. Here's the pixel information on the bottom right there.
Okay, and Lane Karasik has a couple of quick questions. How soon are you going to be publishing the measurements on density, viscosity, etc.?
That's a great question. I ask that question almost every day of myself and our postdocs. So I can tell you that we have a draft manuscript, if Scott's listening, due to me in a couple of weeks. And so look for that to be hopefully accepted and published well before the end of the calendar year. Fingers crossed.
Okay, thank you.